In this video, we're going to work through a full hypothesis testing problem for a single mean. We'll look at one more after this, but let's go ahead and hop in. It says the student academic group on a college campus claims that first-year students study less than 2.5 hours per day on average. So first of all, this is catching my eye, less than 2.5 hours per day on average. One stat student was skeptical of this claim. The class took a random sample of 31 first-year students and found that the mean studying time of 2.11 hours with a standard deviation of 0.75. We'd like to test the academic group's claim using a significance level of alpha equals 0.05. So the steps that we're going to follow are the same as the hypothesis testing steps that we've seen multiple times at this point, which means our first step is to set up what's our null hypothesis, what's our alternative hypothesis. So my null hypothesis, remember that's always going to be a statement of equality. The other thing that we should mention here is that we are talking about averages here. So we're looking at this on average, which means our parameter is going to be a population mean or a population average. That means that our statement should involve the population mean, which is mu. So I've got my null hypothesis. My alternative hypothesis must then also be about mu. I always like to start with the alternative hypothesis, and I'm looking at this claim right here. They're claiming that first-year students spend less than 2.5 hours per day on average studying. So they're saying that the average is less than 2.5 hours. So once I've established that alternative hypothesis, the null hypothesis follows very similarly. I know it's always a statement of equality, so it's going to be the mu is equal to 2.5. So there's my null hypothesis, there's my alternative hypothesis. The other thing that we can do at this point that I think might be helpful for the remainder of our problem is just to kind of lay out some of the information that we have. So if I look at the other numbers that are provided to me, so we've got a random sample of 31 first-year students. That's our sample size. So let's just make a quick note of that. N is equal to 31. What else do we know? We found the mean studying time of that sample. So the mean of the sample, in other words, the sample mean, x bar, is equal to 2.11 with a standard deviation of 0.75. That's the standard deviation of our sample. So, S, is equal to 0.75. And then, of course, test the academics group claim at a significance level of alpha equals 0.05 is our level of significance. So we've got everything that we can possibly kind of wring out of this problem here. We'll certainly refer back to these statistics, but for now, that's a good place to start. My second step, this is something that I should be doing. I should be checking the conditions. Remember, there are a couple of conditions that we should be checking in order for the central limit theorem for means to apply, which is what allows us to do this entire process. We need two things. We need, first of all, independent sampling. Independent sampling is difficult for us to verify, so we're going to use random sampling as sort of a substitute. So do I have some sort of random sampling? And in this case, we took a random sample of 31 first-year students. So yes, we do have random sampling. That part's done. And then the second part, the second part right here is that we need a large enough sample size, or we need the underlying distribution is normal. In this case, n is equal to 31, which is just barely above greater than or equal to 30, which is good. That's what we need. So that condition is also met. This is not generally a step that I'm going to ask you to perform on quizzes and tests and things like that, but it is one that we should be doing each time. Really, the one I want you to be familiar with is the second one, is that n greater than or equal to 30, or the underlying population is normally distributed. So once we've established that, yes, our conditions are met, that means that the central limit theorem applies, we can continue on with our problem. There's never going to be a gotcha question where like, oh, the central limit theorem doesn't apply and you can't do that problem. Haha, joke's on you. That's never going to happen. I'm never going to try and trick you like that. So what else do we know here? I'm going to erase just so we can refer back if we need to. Next up, we need to start doing some calculations. We need to look at what is our standard error, our test statistic, and our p-value. So first up, our standard error, we know the formula for that was s divided by square root of n, and lucky for me, I calculated and laid out all those sample statistics right here. So S is 0.75 divided by the square root of my sample size, which in this case is 31. So I have in this problem 0.75 divided by the square root of 31, and I ended up with 0.135 as my standard error. So there's the first step that I need. Second step is I need my test statistic. So I have to find my test statistic, which I know, of course, is a t-score because we're working with population means. We're using the t-distribution rather than the normal distribution. So t is equal to our sample mean x bar minus mu naught divided by our standard error. So x bar, that was given up here in our problem as 2.11. That part's not really too much of a problem. Remember when we talk about our null hypothesis, mu naught, we're looking at the value that we talk about in our null and alternative hypothesis, which in this case is 2.5. So mu naught is equal to 2.5 here. So we have 2.11 minus 2.5 divided by our standard error. We just calculated that number to be 0.135. So let's see, 2.11 minus 2.5 divided by 0.135. And this time around, I ended up with negative 2.889 as my test statistic. So that's my test statistic. I know I'm going to be using the t-distribution. That's going to be something that I need to reference in just a moment when I calculate my p-value. So I've got that part. A couple small things before I can calculate my p-value. First of all, I need to know degrees of freedom. Remember, degrees of freedom is simply n minus 1. So we said n is 31 minus 1. We have 30 degrees of freedom. We're going to need that number in just a moment. And then the other thing that's really helpful to look back at is what type of test are we performing? And we can get that from our alternative hypothesis. So if I look back right here, if I look back at my alternative hypothesis in particular, we're looking at this part. It's less than, it's a left-tailed test, but in particular, it's a one-tailed test. So this is a one-tailed test. That's going to be helpful for me to know in just a moment. So we're working with this one-tail test at this point, and that should be everything we need. We've got our test statistic, we've got our degrees of freedom, we're ready to go and estimate our p-value. So we can hop over to our t-table at this point. Let's go ahead and start fresh. Actually, if we have 30 degrees of freedom, that means we're looking at a different part of our table. We're going to be looking up here. So we said our degrees of freedom, just to write this down, degrees of freedom was 30, and our test statistic was t equals negative 2.889. So 30 degrees of freedom means I'm looking at this row right here all the way at the very bottom. And I'm going to look for where does negative 2.889 live. Remember that our table isn't going to provide us with any negative test statistics. It only cares about positive. So we're going to use positive 2.889 in its place. And so if I look at it, it's bigger than 1.31, bigger than 1.7, bigger, bigger, bigger. It's actually going to live somewhere over here. It lives somewhere to the right of 2.75. So if I look at what that's going to mean for my p-value then, we said we were performing a one-tailed test, so we're looking at this row of p-values. That means that the p-value lives somewhere, it lives somewhere over here. So if I look at what happens as my p-value moves from the left side to the right side, moving from 0.25 to 0.01 to 0.005, it's getting smaller every single time, which means all I can say at this point is that my p-value is going to be smaller than or less than 0.005. So in this case, hopping back, my p-value, so the p-value is less than 0.005. So that's all I can really say about my p-value. I can't calculate an exact value here, but that's enough information for me to make my decision here at the end of my problem, because we said, let me make sure, we said alpha was 0.05. So comparing our p-value against alpha, which we said was 0.05, I know that my p-value is less than 0.005, which means that it's going to be less than alpha, which is 0.05. So the p-value in this case is less than alpha, or you could say the p-value is less than alpha, which in that case, if the p-value is less than or equal to alpha, that means that we will reject H0. We will reject the null hypothesis. That does mean that we've changed our mind. That means that there is enough evidence to support the alternative hypothesis. So if I scroll back up and look at the alternative hypothesis and think about what this is going to look like for my interpretation, the college campus, the academic group was claiming that first-year students study less than 2.5 hours per day on average. So there is enough evidence to support this academic group's claim. So I'm going to scroll back down here and write out my interpretation before I wrap this problem up. We would say there is enough evidence to support the academic group's claim which we might be able to just stop right there and say there's enough evidence to support their claim, but let's be a little bit more detailed, that first-year students, students, I can spell, spend less than 2.5 hours per day studying on average. So we're just kind of repeating the claim and making sure we say this is what the group is supporting, and there is enough evidence to support that claim. That seems like this is the most likely scenario based on the evidence that's been provided to us. So hopefully these steps feel pretty familiar to the hypothesis testing steps that we saw for proportions and those that we saw from chi-square tests for independence. Obviously, there have been some minor differences here where some of our formulas change. We're using a different probability distribution, but the overall skeleton of the problem is basically the same as we've seen a couple times here. In the next page, we'll look at one more example with what happens if we're not provided with those summary statistics, if we have to go and calculate that out ourselves, which we can use our calculator for. We've done that, but we'll have a quick refresher on how to do that.